And I want you to think about this reaction here. You have a triple bond, and then in the end, you have a triple bond gone, having bromine here. So how would you do it? I mean, since bromine is here, you may think that, okay, this is gonna be you adding a halogen, like a bromine is gonna be added. You add a bromine molecule, BO2, or do you have to add HBr? If you're adding a BO2, it won't be just one bromine. You're gonna have another bromine there, right? So this is something that you need to figure out what you need to be adding. One, definitely, we gotta add HBr. But adding HBr to triple bonds, you're still gonna get the double bonds. But we don't have a double bond there. What that means is another pair is added. That pair is a hydrogen. So we do the hydrogenation and we add an HBr. So we need to have a two different pair to the triple bonds to make this happen. The first thing is you have to analyze what you need to do. Now we realize that, okay, you add an HBr, you're adding an H2, two different things we do. The question is, which one would be first? Or does it matter? Or maybe it may not matter. Or maybe it matters, depending on how you do it. So it's all about your choices in the end, too. Not only recognize what needs to be done, you still need to figure out how they're going to be done. So let's talk about, since you realize that HBr, so HBRs, at least we can add it to the one equivalent, right? Because it comes in solutions. We know the concentration, then we can make it 1-to-1. So one equivalent is just 1-to-1 ratio. Hydrogen is going to go to less substitute side, bromine go to more substitute side. You're going to get this vinyl bromide right here after adding one HBr. Then you got double bonds, so you can basically do the hydrogenations. You can use either platinum, palladium, nickel. I probably wouldn't choose a nickel here for some reason, but that you don't know. So, and then you can do these reactions. So then hydrogenation, then you get that. Let's change the order. Let's say we do it the other way. If we decide to do it, the hydrogenation, with the same reagents here, hydrogen and then platinum or palladiums, this will make a one more of the hydrogen added, you get another one. But under that condition, that will keep going on, and then you get two molecules of hydrogen added, you get this, not that. So this is not the way to go. You have to add just one molecule of the hydrogen. So you have to remember either the lindless catalyst or the sodium and liquid ammonia. That way you get just one hydrogen added, you get double bond here. If this doesn't matter with the trans or cis, because you only need a one hydrogen molecule added, that's the key. It's a terminal condition, so there's no cis and trans here. So even still, we can do that. So you have a one hydrogen molecule added, you get double bonds, then HBr's gonna be added, and you're gonna get this. Question is, I know both are possible. Either you adding HBr and then hydrogenation, or you doing the lindless catalyst and then HBr additions. Which way do I prefer, if you ask me? I prefer second way. I mean, that does not mean that I wouldn't give a full credit for the first answer. I will give a full credit for the first answer, but there's a danger of doing the reaction this way. One equivalent, you add it 1-to-1. Sometimes it's something you forgot. When you're writing the reaction on the paper, you see only one of this, you see only one of that. You think there's just 1-to-1 reactions, but what that actually means, you get 10 to 23 molecules of this, reacting to 10 to 23 molecules of that. That's the chemistry. Sometimes people forget that chemistry happens in number. They don't happen to one molecule to another molecule individual. You got 10 to 20 of this, 10 to 20, and 10 to 23 of that. 10 to 23 is a huge number. When they get mixed together, some of the reagents will react twice, even though you've got 1-to-1 ratio in bulk, but in the microenvironment, maybe there are two molecules available, they just react twice. And then when that happens, some of them will never get reactivated. So you get the majority this, but you get some of them doubly reactivated, some of them non-reactivated, you're gonna get the mixture. So that's not really ideal compared to second step. No matter what happens, this will just make that 100% from that. And then this reaction, only one reaction because you got only one type. So much more controllable. So the chemistry, which routes are much more reasonable, you're gonna figure things out based on how they're gonna do. We try to prevent any of the side reaction happening. So the cleaner the reaction, the better. So it's something that you've got to keep in mind. And obviously, I will still take this one as a right answer. I'll give it full credit because that might be too much for you to bear when you're able to make an answer. But in reality, that's something that you got to worry about. Because chemistry always happens in numbers. Sometimes people just forget that. Because when they write an answer, there's one molecule of this, one molecule of that. You think they're just going to met each other. That's the only thing they're going to do. No, they're going to do so many other things by their instinct. Anyway, so this is kind of one thing that I want to point out using this example. And that was a pretty simple because these reagents already giving you a lot of what's going to happen. That's the mercury sulfate and then sulfuric acid. When they mix them together, there's always water. So what happened was you get the mercury study added on the last substitute side. That makes a vinyl cation. I don't know, some of you actually worry about these things. I keep telling you, as soon as you get the carbocation, you need to worry about the rearrangement, right? Should you worry about the rearrangement of the vinyl cation? Answer is no. Vinyl cation doesn't rearrange. It's different from the regular carbocation sp2 hydrogenous carbon. This vinyl groups kind of makes this one non-rearrangeable. So you don't have to worry about the rearrangement of the vinyl cation. So that's going to stay there, and that's going to be captured by the water. So you get vinyl alcohol. Most likely people just stop there and write that as an answer, but I keep telling you that is not the right answer. You need to think about vinyl alcohol will change its form to the ketone form. That's ketotautomerisms, make the carbonyl, and these ones get protons, you get the ketones. This ketotautomerism, it sounds very non-important. It's just happening only this reaction. You're gonna think again. The very last chapters of Chem 2, we're gonna come back to this concept again, ketotautomerisms, and then try to use that for the reaction in a very different kind. So this will come back to you again. It's ketotautomerisms. So you really need to remember these things for a long time after this. If you decide to use not this, cyanoborane, then you're going to add the water, but because of the borons involved, it's going to make anti-molecular addition. The base is orientation, hydrogen and OH is going to be swapped. OH go to the less substitute side is all because boron goes to the less substitute side, and this one's a really huge boron, the dialkyl borane. So the boron goes to the less substitute side, more substitute side gets the hydrogen, and this boron will be replaced by the OH in the oxidation step. Then you get the OH here, but this is a vinyl alcohol again. Don't write that as an answer. You got to change the ketone forms. That comes in, make a carbonyl. This comes out to make out the proton. You get that out there. So depending on how you do it, you don't get an alcohol. You get either ketone or the other, depending on what you do. So we love this question. We always look at this question in the final. So I'm pretty sure that after that, these things are pretty simple to figure out. You got a triple bond here, you are having an aldehyde. I know these things are not easy unless you know these tautomerisms. That is a thing. It's really hard to figure out what to do if you look at this way. In most of the cases, we look at what changes are made, right? It's a double bonds here. When this side have an OH here, when that is added hydrogen, we can figure out, okay, waters are added. And then what reaction do you know to adding water? And then you need to look at where the wage groups there, if the more that's up to the side, then that's going to be the hydroboration. So you can figure things out that way with the double bond. But in the case of triple bond, that vinyl alcohol will change the aldehyde. So this is something that you gotta remember, the enol tautomerism, to see that this actually came from the enol. That's the part that is very hidden. So it's not very trivial when you see in the other direction, find out the right reagents. This is done by the hydroboration again. That things we discussed. So that makes an aldehyde there by making an enol OH and a double bonds between OH. This is basically you got the boron goes less substitute to the side, hydrogen goes more substitute to the side, but the boron replaced by the OH. This is basically what makes it change this form. So if the question is when I show this, how to make that one from here, then you can figure out hydrobораtions, but I show you this. So this part is something that you have to measure. So this is kind of a little bit more difficult because it's kind of hidden in that way. So that's something that I really need to warn you. Enol tautomerism is something that it may really make you off balance very easily. All right, the ozonolysis or the permanganate in the high temperatures or basic condition will break the triple bonds, and then either end is going to become carboxylic acid. Very, very simple. So it's going to the benzoic acid to the left side. The right side is going to be the carboxylic acid that forms. So that's a simple thing. Ozonolysis is pretty simple with these triple bonds.